So, let us look into an example of putting this concepts of multivariate optimization to use in the context of infrastructure systems. In this problem, we will try to design a levee. So, if you are not familiar what a levee is typically a high embankment provided on either side of water carrying structure, for example, river or canal that would raise the capacity of that particular water body, so that when there is a flood like situation, that water body like river or canal can hold more water in it. However, you can imagine that if you have to design a levee along length of the river or for a particular stretch running through the city, it would entail money. So, you would want to optimize the dimensions of that particular levee so that the costs are minimized. However, these levees are also structural elements. So, you have to give them dimensions appropriately so that the structural integrity or stability is not compromised. So, here is a problem where we are said that an engineering firm is designing a levee along a river bank to prevent flooding. The levee must have a trapezoidal cross section. So, if I draw the sketch, it should have a trapezoidal section like this, and we can expect water to be present somewhere here. It has some top width T, it has some base width which is equal to B, and height is fixed for us which is equal to 3 meter. So, we will not optimize for height, but we will optimize for top width and bottom width. Now, it is also given that levee extends for the length of 5000 meters, or we are designing it for 5 kilometers, perhaps covering entire city. Now, various constraints are given to us. Remember, so far we have only learned unconstrained programming, but an engineering problem may have certain constraints specified. So, we will see this example that based on what we have already learned, how we can still solve this particular problem without using any additional mathematics. In subsequent lectures, I will discuss methods to explicitly account for these constraints in your mathematical formulation, but right now we will just be aware that these constraints exist, but without changing our mathematical framework, we will still try to answer the key question that would be asked to us. So, it is said that this T should be greater than 1 meter and base should be greater than 4 meter. Now, as I mentioned that if the dimensions of your levee increase, the total annual cost for building and maintaining the levee is also going to increase. So, it is 50 times the volume, it is 200 times the base area and some other parameter which depends on the length and the top width of that particular levee. Now, if you see that there is a volume term involved, volume is going to be area multiplied by length, and we already mentioned that this particular levee is going to have a shape of trapezoid. So, trapezoid would have an area of base plus top divided by 2 into height, and width of the base is given to be B and total length is L. So, SB, that is base area, would come out to be B into L. What we know in this particular question? We know L, we know H because this is fixed, but we do not know B and we do not know T. However, we have some constraints around B and T that we will try to see how to incorporate into our problem. So, what is the problem at hand? Problem is that determine those values of B and T that minimize the total annual cost. We are also asked to verify the necessary and sufficient conditions for a minimum are satisfied by computing the gradient and the Hessian matrix. Let us see how far we can go into this particular problem, if at all it is possible to apply all the math to a real problem. So, here is how a typical levee looks like. If you have not seen levee, that if you see that there is a river here, there is a road here, and this particular stretch is artificially raised, and this is what we mention as levee, and it does cost money because we have to ensure that the water does not seep through to the highways through that, and also we have to make sure that the vegetation cover is maintained to certain optimal, regular maintenance would happen so that there are no gully formation into these particular levees, otherwise they may result in entire slope failure and the purpose may be defeated. So, if this is clear, let us start putting the solution together. First of all, what I will do, I will write the cost function. So, what is given to us, that cost function as function of B and T is equal to 50 V B times T plus 200 time SB plus 1000 L by T. Now, V is given to us as A cross L and area is given to us as B plus T divided by 2 into H, and H is given to us as 3. So, this reduces to B plus T divided by 2 into 3, and volume of this levee would come out to be A, which is function of B into T multiply by length of the levee, which is again given to us as 5000, and base area would be simply B multiplied by length of the levee, which is 5000, and we have substituted all the values here. So, now I can put all these components of A, V and S into my equation 1 that I am currently highlighting and numbering as 1, and get this in a form of 750000 B plus T divided by 2 plus 1 million B plus 1000 into 5000 divided by T. Now, this is the cost function which is bivariate. So, whatever we do here would also apply to multivariate conditions. In this case, it is restricted to B and T. Even if it is function of H, I will also have one H term which is not needed here and so on. But the fundamental remains same, that to satisfy to meet the necessary conditions, what I will do, I will take differentiation of this with respect to T and equate to 0. I will take partial differentiation of cost function with respect to B and equate to 0. When I take the partial differentiation of C with respect to T, I get an equation of form 375000 minus 5000 into 1000, which was product of the constant multiplied by the length as we saw in previous equation, and when I equate it to 0, I get value of top width in this case as 3.65 meter. I am not going to solve this for you, you can check it for yourself as part of the homework, but we get T is equal to 3.65 meter. However, an interesting thing would happen when we differentiate this expression, the expression that we derived earlier with respect to B, and we will only get a term which would give us the value when we equate it to 0, this would come out to be some constant which cannot be solved for B. Now, what does that mean is that this necessary condition is satisfied when we partially differentiated with respect to T. However, partial differentiation with respect to B does not give us any clear answer. Now, if necessary condition is not met, there is no point in checking for sufficiency condition. So, we have to practically go back to our question or problem and identify what is the best decision we can take, even if we hit this mathematical infeasibility purely from mathematical side. So, one thing is clear, that there is no doubt about H, there is no confusion about T, but B is not giving us clear answer. So, that also means that it is not possible to optimize the given mathematical function in B. So, what we will do, we will go with the constraints where we said that the B should be greater than 4 meter and the boundary condition should give us that particular answer, that to ensure structural stability, if we provide B is equal to 4 meter, that is not violating any constraint. Although that is not necessarily minimizing the cost here, but going by the necessary condition, this is the best decision that we can take to provide a particular B. Also, we come out with certain top width is equal to 3.65 meter. There was a constraint that top width should be greater than 1 meter. We have already met that particular constraint. So, this also holds true for the decision that we are taking. So, we have all decision variables in place now, that h is equal to 3 meter, t is equal to 3.6 meter, and give B is equal to 4 meter. With these dimensions, you can go ahead and design the levee, and the cost associated indeed is going to be minimum under the information that has been provided. So, this example clearly tells us that wherever possible, we should stick to our fundamental derivation, fundamental understanding of necessary and sufficient conditions, but in real world we will often hit the points where the necessary conditions are not being met, but still we have to take an informed decision, account for the information that has been given to us, and in such cases these constraints does help us take these particular decisions. Now, this is a simple problem, I would say, where constraints were simple values. However, in other situations we can have these constraints specified in form of equations, multivariate equations. The objective function is also multivariate. These constraints can be equality constraints, that is, they have to be exactly equal to certain value. For example, here we can say that that h equal to 3 meter, it's a hard constraint that it has to be met. Although h did not participate in our decision making of cost, because we already fixed it that particular value. However, in many cases these hard constraints may be present in functional form rather than just the explicit value like h equal to 3 given to us. So, even in those situations we have to take the decision, we have to account for all these constraints, both equality constraints and inequality constraints, which is going to be a very important part of our discussions as we go forward. So, in next lecture we are going to touch upon these concepts of multivariate optimization with equality constraints, and subsequently we will move on to multivariate optimization with inequality constraints. So, let us continue our discussions with the new topic in optimization, what we call as constraint optimization problem. In our last discussion, we already looked into this example of levee, where our objective was to minimize the cost of construction of a 5 kilometer long levee, and we were asked to optimize the width and width at the base and at the top, so that the overall costs are minimized. However, you might have noticed that there were two additional constraints that were specified, that is that base width should be greater than certain meters, top width should be greater than certain meters, and height is given as a fixed value of 3 meters. In optimization world, these three equations when written mathematically are called as constraints on optimization problem, and they have to be included into the process of finding an optimal value systematically, and maths will take a different form that we are going to discuss in this particular module. So, the outline of this discussion is that we will start with equality constraints, then I will introduce the concept of Lagrange multipliers, then we will see that how necessary and sufficient conditions changes when constraints come into picture, and how Lagrange multipliers can also be dealt into this necessary and sufficient conditions as we solve these problems. So, let us state this constraint optimization problem with equality constraint in mathematical form. Now, we have to minimize the objective function f x. Now, this x again can be vector as x1, x2, x3 and so on. So, we are looking for minimizing f of x1, x2, x3 and so on, and for mathematical compactness we often write this as f of x vector. Now, this is not standing alone. If you compare it with unconstrained optimization, we will just stop it here, minimize fx, and we will start doing the differentials, equate it to 0 and get our answer. However, now there is an additional condition that is satisfied, that it is subject to another function gx equal to 0. We will look into very specific examples. So, you need not worry if you are not able to fully comprehend this mathematical notation, but this is important to state in its general form because it would apply to 2 variables, 3 variables, n variables and so on, which is more practical in the engineering sense. Now, this gx itself can also be vector with multiple constraints stated here. For example, we can say that minimize some function x square y subject to x square plus y square equal to 1, x equal to 0.5, y is equal to 0.75 and so on. Right now, I am not worried about whether these constraints are simultaneously feasible or not, but this is essentially what would constitute this gx vector, where your x vector has 2 elements, that is x and y. That is why our objective function is function of x and y. Constraint number 1 is function of x and y, second constraint is function of x, and third constraint is function of y. Again, I am saying that we are not commenting on feasibility, we are just stating it mathematically. As we go towards the contextual problems, we have to also ensure that these constraints are not ill stated. What may happen is that we may write a constraint, but it is not compatible with the other constraint. One example is that x should be equal to 0 and x should be equal to 0.5. Now, we know that x can either be equal to 0 or equal to 0.5, and these two constraints are incompatible with each other, or we also say that the problem is ill stated, it is not well stated because of the incompatibility of these equality constraints. So, what we do here is that there are multiple ways to solve these particular problems, specifically when we are dealing with equality constraints. One way is that we can go with substitution and convert unconstrained problem into a constrained problem into an unconstrained problem. We can convert problem with constraint into non-constraint problem, and we will see that with help of an example, but let us state the mathematics first, that if we have gx equal to 0, we can write x1 as function of every other variable but x1, and we can substitute x1 back into the original objective function f, which is also function of x1, x2 and so on. And now we get an objective function which resembles our unconstrained optimization form, and all the necessary and sufficient conditions can be applied easily, because the information of constraint is now encapsulated in variable x1, because x1 is having the information from constraint itself, and hence even it looks like an unconstrained optimization problem, the constraint has been embedded into the objective function itself. So, we have already learned how to find maxima and minima for unconstrained problems, that is, we will take partial differentiation with each variable equal to 0. Then we will check the sign of Hessian to check for sufficiency, whether the point is indeed minimum or indeed maximum, and we will have our answers. One very simple example is that we have to minimize a function x square plus y square. If you recall, this x square plus y square equal to a square resembles a circle, but if I state this as an unconstrained problem, if I say that minimize x square plus y square, you would say that in real domain answer is 0, because if you provide x is minus infinity, or y as minus infinity, this particular value will become infinity, and hence that means that negative values are not helping us go towards the minimal. So, we will find the minimum value of this function at x equal to 0, y equal to 0. So, the minimum value is 0 at x equal to 0 and y equal to 0. However, now there is a constraint, that is we have to find minimum value of function when x plus y is equal to 1. That is, if I draw a line y is equal to minus 1 minus x, this line would look something like this. In fact, this would be with a negative intercept, this is minus 1 and also slope of minus 1. So, it would pass something like this, and then there is a circle that I want to minimize. So, I will just place a circle representative of x square plus y square, and I have to find a minimum value such that the solution lies exactly at the point where this x plus y equal to 1 is also satisfied. How we do that? We will also get some geometric sense for that, but right now if we go by mathematical substitution, what I can say that y is nothing but it is 1 minus x, and so in fact if this is 1 minus x, we can shift it upwards, because in that case intercept is going to be positive, but still the reasoning remains same, that there has to be an intersection of the circle and y and the line stated as x plus y is equal to 1. Now, if I substitute y is equal to 1 minus x, I reduce this objective function as f x equal to x square plus 1 minus x whole square, because y is substituted in terms of x and f x simply becomes 2x square minus 2x plus 1. So, if our original objective function was x square plus y square, the equivalent unconstrained representation of a constraint problem now takes this form, and we already know how to calculate its minima or maxima. We differentiate it with respect to x, equate it to 0, and we see that at x equal to 1 by 2, we get one of the critical points. Now, when x equal to 1 by 2, we can also substitute y as 1 minus 1 by 2 and find that y also comes out to be 1 by 2. So, the minimum or maximum, I do not know yet because I have not checked for the sufficiency, but one of the critical points for this objective function is 1 by 2 comma 1 by 2 when this constraint has to be met. So, in unconstrained optimization, our answer was 0 comma 0. The moment constraint comes into picture, we have a new critical point of interest, which is not 0 comma 0, but 1 by 2 comma 1 by 2, because of this method of substitution. Now, sometimes substitution works, sometimes substitution may not be, we may not be able to use substitution when variables are not separable from each other. In that case, we need much more generic tool that help us navigate through the problems where achieving variable separation is not that easy. In that case, we use a very interesting concept of Lagrange multipliers, and let us try to build some intuition that what are these Lagrange multipliers, what they do, how they help us solve the problems of optimization, and these Lagrange multipliers will be used throughout the modules of optimization as we cover our journey to linear programming or sensitivity analysis or shadow price analysis. So, I would request to pay detailed attention to this concept and try to solve a few problems to get full grip on Lagrange multipliers. So, what Lagrange multipliers do is that if we have a problem stated as minimization problem of f of x subject to some equality constraint, then Lagrange function says that we can come up with a new function which is f of x plus a term lambda multiplied by g of x. If you see, this lambda is also a vector. if we are dealing with multiple variables, and as a result of which, to ensure the multiplication compatibility, we introduce this notation of transpose. Now, if you have this Lagrange function stated, this again becomes a problem of unconstrained optimization. Whatever we were doing with the unconstrained optimization to find critical points, we can do exactly same treatment with Lagrange multipliers, that is, take its partial derivative with respect to x, take its partial derivative with respect to lambda, equate it to 0, and we would solve all these equations simultaneously and get our values of x, y and lambda. If you notice one thing, when you differentiate this equation with respect to lambda, you get the original constraint back, which is gx equal to 0, which has to be satisfied. So, what does it mean? That even when we introduce a multiplier from minimum fx subject to gx equal to 0, Lagrange multipliers do not change the fundamental aspect of the original problem that has been stated, because we retrieve our original constraint back while doing the differentiation. So, now this mathematics is fine. What is the intuition behind that? Let us pay attention to that. So, again I have stated this particular equation, set of equation in much cleaner way, but let us see what it does. Let us say that we have a problem. I'll go to a nice graphical representation in the next slide, but first of all let us design the problem here and try to apply our thoughts that how this is this Lagrange multiplier is coming into picture. Let us say that I have a function which is maximize x square y, and it is subject to some equality constraint of x square plus y square is equal to 1, and we have to find the maximum value of x square y. If I go in unconstrained setup, if I put x equal to infinity, y equal to infinity, maximum gains that are possible are infinite. Why? Because it is a positive function in x and y, and I just put two values and I get my answer. However, now there is something that is holding me back, which is x square plus y square equal to 1. That I now cannot go for infinity, I have to search for my answer along this curve, which I know is a circle of unit radius. Let us try to draw it mathematically and see that what this Lagrange multiplier is essentially telling us, and why these gradients come into picture. So, if I draw the contours of x square y, they would look something like this. They will be all these quadrants, but they would be something like this, and so on. And this would be increasing in this direction. So, this is direction of gradient of f, because I am calling this as fx and I am calling this as gx. I should use vector notation. Why? Because x and y are involved. So, I should not just say this function of x, and I can say that x vector comprises of x and y. Now, it is increasing in this direction, and I have one constraint sitting right here, which is x square plus y square equal to 1 in equation of circle with center equal to 0, 0. Now, if this is clear, I have to find for that contour of x square y that satisfies the equation of circle, because it is an equality constraint. If I am not touching the circle at a point of interest, that means I am violating that particular constraint. For example, it is very clear that if I draw another curve x, this is also x square y, let me draw it a bit nicely, this is also x square y. These 2 points are indeed satisfying the equation of circle. However, value at point that I have crossed in red is lower than the point in green. So, I should go with green. However, my constraint would not allow me to go for green. So, I have to look for my answer in vicinity of this red cross that I have drawn here. So, what I will do, I will start finding a contour something like this that just touches this particular circle, or in another way which is just tangential to my constraint. Now, what happens here? Here, whenever you have two curves that are tangential to each other, their perpendiculars or normals, they are parallel to each other. And this is exactly what Lagrange multiplier is trying to say. That is, when you take the gradients with respect to x and equate it to 0, you are essentially saying that gradient of f of x is indeed equal to lambda times gradient of g of x, or gradient of f of x is proportional to gradient of g of x. That means they are aligning in the same direction. When we talk about equality constraints, we have no problem with sign of lambda. They can be parallel, they can be anti-parallel. So, lambda is unconstrained in its sign when I am talking about the constraint problems with equality constraints involved. However, the key takeaway is that I am interested in that particular contour that just touches it at the point of tangency to the constraint that is specified to me. And when that happens, the gradients are proportional to each other. And one way to remove any sign of proportionality is to introduce a constant. And in this case, I introduce a constant and call it by a special name that we call as a Lagrange multiplier. And when we go to constraint problems with inequality constraints, then lambda's sign has to be checked as well. So, the statement that I make that sign of lambda is unrestricted only applies to optimization problem with equality constraint. So, that is what we will keep in mind, but we are interested in this point of tangency. So, I wrote a small Python code for you to create a nice illustration that what I am essentially meaning about this point of tangency, that I generated hundreds of contour lines of x square y. You can see that some of them are passing through inside the circle, some of them are outside the circle, and so on. So, whatever contour lines are outside the circle are of no interest for us because they are not meeting this circle at any point, and hence they would be for sure violating our constraint. So, what remains for what remains interesting to see for us are lines like this or lines like this, on this side lines like this, and so on. So, this is where one of our feasible answers will lie, and then try to see what is happening. One thing is clear, that our function is increasing in this direction and gradient points in the direction of fastest increase. So, this is also increasing in this direction. Again, this is the direction of fastest increase, that if I have to increase value of my objective function, I should start walking into this direction because that is the direction of gradient, and we represent this by del of f, or partial derivative of f with respect to x, partial derivative of f with respect to y, and its collection will become the gradient vector of f itself. And we clearly see that the maximum value happens at a point which is just touching this particular circle, or the contour line just kisses the constraint variable or the curve traced by the constraint, and that is the point of interest for us when we talk about these problems. So, what we see is that at the point where our contour line touches the circle, value is 0.38, similarly we will get value of 0.38, this function is symmetrical about y, so you will have value of minus 0.38 on other side, and so on, and we get these maximas and minimas when you just look into these plots. Now, summing this into our mathematical framework, our objective function was x square y subject to x square plus y square equal to 1. We write a Lagrange function as x square y plus lambda 1 minus x square minus y square. In some books you will also see it is written as x square y minus lambda 1 minus x square minus y square. In case of equality constraints, this will not create a problem because lambda is unrestricted in its sign, whatever sign you give to it, that is not a problem. So, these two conditions are equivalent to each other, only thing is that sign of lambda would be different. We take this differentiation of lambda with respect to x first, equate it to 0, partial differentiation of lambda with respect to y, equate it to 0, partial differentiation of lambda with respect to lambda and equate it to 0. Solve the equations, we get x equal to 0.82, y is equal to 0.58, and at that point we find value of this particular function as 0.385 by substituting x as 0.85 here and y is equal to 0.58 here, taking square and multiplying with the value of y, we get our answers. So, if this intuition is clear to you that gradients of the objective and constraint align at the point of tangency and the objective's contour is tangent to the constraint boundary, Lagrange multipliers become much easier concept to deal with in optimization, in various concepts of data sciences and machine learning and as well as linear programming problems. So, this intuition that you will always have optimal points or critical points at points of tangency has been used to derive multiple interesting results that we will talk subsequently in our discussions. So, again when we if we now put everything in the context of necessary and sufficient conditions, whatever we have learned so far can be stated that these are the necessary conditions with Lagrange multipliers, that is there should be a stationary point condition being met, that is partial differentiation of Lagrange with respect to the constituting variable should be equal to 0, partial derivative of Lagrange function with respect to lambda should be equal to 0, that gives us the constraint satisfaction, and all these equations are solved simultaneously to give our answer. We already looked into this particular problem, but I would still request you that solve this particular problem without the help of notes or anything, and try to see whether you get the answers that I have derived earlier to get absolute clarity that what these Lagrange multipliers entail. So, now moving ahead, next condition that we have to look into is what we call as the sufficiency condition. So, the mathematics of this sufficiency condition is bit more involved than the sufficiency conditions of unconstrained optimization, but we will try to identify what are the common elements across these two set of problems and why there are certain distinctions from unconstrained to constrained optimization problems. So, if you recall, we were talking about Hessian metrics when we started our discussion about sufficiency condition in unconstrained problem. Here also we talk about the Hessian metrics, but instead of the objective function f, in case of constraint optimization we start talking about Hessian of Lagrange, and we were testing for the positivity of the term which is given by H transpose Hessian of f multiplied by H when we were talking about unconstrained problems. In case of constraint problems, we would still look for this condition to be greater than equal to 0 for point to be minima, not equal to 0, in fact greater than 0 for point to be minima, less than 0 for point to be maxima. However, there are certain adaptations that we have to do to this mathematical form, that we write this as D transform HLD greater than 0 for this point to be minima and so on. Now, what this D and H differs what this and the Hessian term remains same. So, we would not worry about that, but what is this distinction between D and H? Let us try to understand that, and why we introduce a concept called as bordered Hessian matrix. So, instead of using pure Hessian matrix, we would be imposing a much strict constraint. I would use two words, direct Hessian, which we used in case of unconstrained problems, and another term that we are going to use is bordered Hessian, that is typically associated with Hessian of lambda, and we use it for constraint problems. Now, when we were talking about this direct Hessian, we were saying that we will expand our function around a small perturbation h. So, f of x plus h would be written as f of x, then first differentiation, then second derivative multiplied by h square upon 2 factorial and so on. But when we were talking about unconstrained problem, this h was perturbation in any direction. It can be on left side, it can be on right side, it can be in forward direction, it can be on backward direction, because the term itself is unconstrained. If your objective function is unconstrained, so would be the perturbation that we are making around the point of interest. However, the moment we start talking about constraint optimization, the direction of perturbation also get constraints along the constraint that you have to satisfy. So, if we go back to the earlier example where we were looking into this plot, I will just clear it up to reduce some clutter here. If I am interested to see whether the point that I have obtained here is indeed maximum or minimum, I no longer can perturb it in this direction or this direction. This perturbation is simply not allowed, because the moment I perturb it in this direction away from the circle or inside the circle, I am immediately going to violate my constraints on equality. So, I am only left with perturbation on either on the left side or on the right side of this point of interest, so that at any point I am not leaving the equation of constraint. That is why when we start talking about constraint optimization and its Lagrange, we introduce the term of D instead of H, where D is in the direction of the constraint itself, to ensure that we introduce a secondary check that if D is a very small perturbation, its product with the gradient of constraint should be equal to 0. To make sense of it, let us say that my G is simple function in x, the gradient of G would simply be del G upon del x. If I do a small perturbation, let us say del x dash, to ensure that this indeed is in the direction of my constraint, this product should be equal to 0, and this is exactly what this condition is taking care of, that we are only moving in the direction tangential to the original constraint. Now, doing all this in mathematical way is possible, and we will look into one example here, but for mathematical convenience we use a modified form of original Hessian matrix, what we call as the bordered Hessian matrix. So, let us look into the components of bordered Hessian matrix without worrying about the detailed derivation how we reach here, because in the course of infrastructure our objective is to use these particular concepts with great intuition to solve the problems. However, if you refer to a standard mathematical book, you should be able to find the derivation, that how we go from a Hessian matrix to bordered Hessian matrix in much more detail, but that is not within the scope of our discussions in this particular course. But what these elements of bordered Hessian matrix would be? There would be Hessian matrix of original Lagrange multiplier, what we will call as H of L, which is nothing but double derivatives of H with respect to x and y and z that would be arranged along the diagonals, and double derivatives with respect to the variable x and y, y and z and so on arranged in the matrix form. Then on top we will be bordering this Hessian matrix with the gradient matrix of G of x and gradient matrix of G of x transpose. So, transpose goes here and the original matrix goes here, and to ensure that it remains a square matrix, we will be padding it with 0, padding with zeros. So, again I have written this in bold. So, a bold 0 would mean in this case that we are essentially talking about a matrix of size m cross m, where m is the number of constraint that we are dealing with. So, if it is one constraint, we will only have one 0. If we have two constraints, we have to pad it with 0, 0, 0, 0, and G of x will come here and its transpose G of x transpose will come here, and the prime matrix which is Hessian of L would sit somewhere here. And then we say that this bordered Hessian matrix is of interest for us, and we have to look into the property of bordered Hessian matrix to establish whether our point is indeed maximum or minimum. The broader understanding remains same, that if our bordered Hessian matrix is positive definite, that means the entire term D transpose del square of Lagrange into D is greater than 0, that would give us point corresponding to minima and vice versa. But instead of getting into trap of calculating eigenvalues, we would use a different way to check for positive definiteness of the bordered Hessian matrix in form of leading principal minors that we will discuss next. So, now let us look into that how we will check the sign of determinants for the leading principal minors to establish whether our bordered Hessian matrix is positive definite, positive semi-definite, or and so on. So, what it says is that we will look into these determinants of various minors, that is if you have two constraints, let us say, then for k equal to 1 to k equal to 2, you would end up with two matrix B1 and B2. So, first minor, second minor, and they have to be equal to 0, which would certainly be the case because we are padding this matrix with the zeros to make sure that it remains a square matrix. What is of more interest to us is to see that how the sign of determinants of m plus 1 and n plus 1 changes as we check for this positivity or negativity of the bordered Hessian matrix. So, if you recall, one way to check for the determinants of leading principal minors is to look into minus 1 raised to power k determinant of Bk greater than 0. What it does is that if k is odd, we have minus 1 raised to power k as minus 1, and if k is even, so for k even we have this as minus 1 raised to power some even number, I am representing it by k star, comes out to be 1. So, it is not just the sign of determinant of Bk where k is from m plus 1 to n plus m, where n are the number of variables. So, m are the number of constraints. So, we will check for constraints plus 1 to number of variables plus number of constraints. So, if we have 2 constraints, we will have m equal to 2. If we have 2 variables, n become equal to 2. So, we would check for k equal to 3 to k equal to 4, and both of these should follow this sign. That is, when k is equal to 3, this number minus 1 raised to power 3 determinant of bk should be greater than 0. And how this would be greater than 0? If determinant of bk is less than 0. So, when you are checking for odd k, so I'll write it here. When we check for odd k, determinant of bk should be less than 0, and when we check for even k, this determinant should change its sign, and hence when we look this into the product of minus 1 raised to power k and determinant bk, we would have alternating sign of determinant of bk, but overall sign will remain consistent, that is greater than 0. And if this entire value is greater than 0 for all k's from m plus 1 to n plus 1, n plus m, what we have is that this point is guaranteed to be minima, given that necessary conditions of gradients equal to 0 for Lagrange are met at that particular point. We will also look into an example with all mathematics done. So, no need to worry if you have missed that how to actually calculate the signs, etc. So, once we do that particular example, that fundamental will become very clear. But still it is important to learn the generalizable mathematical functions, that what is happening in the background as we are checking for these necessary and sufficient conditions. There is another way to check for sufficiency, which is much easier to state than the bordered Hessian matrix. However, advantage with bordered Hessian matrix are that they are incredibly easy to solve for computers, because checking for these lower rank matrices, their determinants is very intuitive way to check for the positive definiteness or negative definiteness, but we can also go by the first principle of feasible directions, that instead of using these bordered Hessian, we can directly verify that this D transpose multiplied by Hessian of Lagrange multiplied by D vector should be greater than 0. This was our primary condition, by the way, in combination with that the null space of del gradient is equal to 0. That means, if we move a small perturbation in the direction of g x, which is in the tangential direction of g x, we are not leaving the curve, and if this condition is satisfied, we can also ensure the positive definites of H L along the feasible direction D, and that ensures that our point indeed is minima. So, one interpretation of this entire mathematics is that only movements along the tangent space T x are permissible without violating constraints to first order. Because when I am talking about gradient of g x, I am essentially talking about direction of the steepest change. However, when I am talking about moving along the feasible direction, that is along the curve, I am talking about moving along the tangential direction, and this happens to be the null space of the gradient g x itself, and hence this multiplication of del g x by d ensures that I am never leaving the curve and hence never violating the constraint to first order. Another interpretation to that is that this positive definiteness ensures that any infinitesimally small movement within this Tx increases the Lagrangian, and whenever Lagrangian is increasing, that means the original point x star indeed happens to be the local minimum for us. So, putting this all together is that these feasible directions do lie in the null space of this gradient Gx. That is why this gradient of Gx multiplied by d was coming out to be 0 to satisfy this condition of feasible direction being in the null space. Second thing that we learned is that bordered Hessian metrics give us a practical way to compute for sufficiency conditions, and in both cases, no matter what, how we are arriving at an answer, we are essentially behind the term called as positive definiteness to confirm whether a point is local minimum or not. Now, when we will solve the problems related to infrastructure engineering, we would definitely be using computers and codes and so on, and most of the times we would not be doing this mathematics manually, as computers are there to help us in our decision making process. But it is of utmost importance to know that what these computers are doing in the background, what are the values associated with my answers, and whether it is even right or not right, and if I have to do second order inferences, all these mathematics become very handy even if you do not have to solve these particular problems by hand. However, to gain clarity of bordered Hessian metrics or checking the directions along the feasible curves, I have solved couple of problems for you from both the methods. Again, it is our standard problem that we will use time and again, is that let us maximize the function x square y subject to a constraint x square plus y square minus 1 equal to 0, and we have to use Lagrange multipliers to find the critical points and determine the nature of each using second order conditions. The reason I have specifically mentioned that use Lagrange multipliers, because whenever we see any equation in 1D or 2D, we are always tempted to plot the graph, find the contours and the intersection of it at the point of tangency with the original curve, and we get an answer. Yes, it works absolutely well when we are talking about f of x or f of x of y. But now if we have to deal with multiple variables such as x, y, z, x1, x2 and so on, it would be impossible for us to visualize this in multiple dimensions, and hence this mathematical formulation becomes handy if it cannot be visualized on graph paper and so on. So, the first step, as always, I think this is the fifth time we are writing this Lagrange function deliberately, just to emphasize that how important these Lagrange multipliers are in the context of optimization. So, never hesitate to write them again and again when you are dealing with equality or inequality constraint. So, in this case I write it as x square y minus lambda x square plus y square minus 1. I can also write it as x square plus into y plus lambda x square plus y square minus 1, again emphasizing that these are equivalent statements, because in this case lambda is unconstrained and so on. So, these two are equivalent. So, do not get bothered if we go with some different form in different problem and so on, but only for equality constraint. So, the first step first, what we do is that we compute their partial derivatives with respect to x, their partial derivative with respect to y, and partial derivative with respect to lambda, and equate it to 0. As you see that in case number 3, we get our original constraint back. Here we get functions of x, y and lambda for both equations 1 and 2, but our math remains simple, that we set these derivatives to 0 and find the critical points. Now, what may happen in this case, that lambda and x, they are coming in multiplied forms and so on. So, achieving a clear variable separation may not be possible, but good thing is that we have as many variables, as many equations. So, this system can definitely be solved even if we are unable to separate the variables with respect to each other. So, what we do is that we make various cases. In first case, we put x equal to 0. When we put x equal to 0 in this equation number 1, we get y is equal to lambda or x equal to 0. So, if we simplify equation number 1, we get with x into y minus lambda equal to 0. That gives us that we can have x equal to 0 or y equal to lambda, and that is what our case 1 also corresponds to. So, when case 1 could be that either x equal to 0, when x equal to 0, we end up with equation number 3 giving us that y could be either plus minus 1 and lambda in that case would be equal to 0. Whenever Lagrange multiplier takes the value equal to 0, that also means that our constraint in that case has become inactive. We do not have choice of an inactive constraint in equality setup, but these inactive constraints would become an important parameters to check for when we talk about Cohen-Tucker conditions in our subsequent modules. So, this was the story of case 1, that we end up with these 3 possibilities, that x equal to 0, y is equal to plus minus 1 and lambda is equal to 0. And similarly, we can have the second case where y is equal to lambda, because y minus lambda is multiplied by x equal to 0. So, one of them have to be equal to 0. So, what happens when y is equal to lambda? In that case, we get using a very similar methodology. Again, I will not worry about the mathematics, I will worry about the inferences that we are going to draw from this particular system. We get lambda is equal to plus minus 1 by root 3, y is equal to lambda and x square is equal to 2 by 3, and these appears to be more interesting solution than the previous one, because in previous one we are ending up with an inactive constraint, which again is not a choice when we are dealing with an equality constraint problem. So, this case 2 appears to be more pragmatic to deal with, because if x equal to 0, we end up losing the constraint which we do not want. Hence, we stick to this particular value of y is equal to lambda, and we get the following critical points, that is 0 comma 1, 0 comma minus 1 with lambda equal to 0 would be of least interest for us. However, other points with lambda is equal to root 3 by 3, lambda is equal to minus root 3 by 3 would be points of interest, where we get these values as root 6 by 3, root 3 by 3 and so on. And when we look into these particular values, we will check which point corresponds to maxima or minima, and to do that we have to check for sufficiency, and we will use 2 pathways. One is actually check the sign of D transpose Hessian of Lagrange D, and second is we will actually construct the bordered Hessian and check for its sign of various ranked, in fact low ranked matrices that are embedded into that. What we do with one point can be also generalized to other points. So, we will look into one of the points. So, let us consider the point root 6 by 3 and root 3 by 3 as our point of interest for these calculations. We get the value of function f as 2 root 3 by 9 and at other points we get the same value for minus root 6 by 3 and root 3 by 3, because our objective function is x square y. So, if x is positive or negative, we are going to get the same value of objective function. If we change the sign of y though, we will get negative of above, and hence we are looking at two values, which is 2 root 3 by 9 and minus 2 root 3 by 9. We certainly know that since all necessary conditions are met, this corresponds to local maxima, one with negative value corresponds to local minima, and all conditions are being met here. So, these are the 2 points of interest. Again, if we talk about the points 0, 1, 0, -1, they do lie along they do touch the circle, because the third equation is also being satisfied, but that is not strictly the point of tangency, as a result of which we end up with the trivial solution if any of these x and y equal to 0, that we get the values of function at critical point to be 0, but a higher value than that exists, the lower value than that exists. So, we are not going to talk about those original points in our discussion. So, next is that we now will go to check for second order sufficiency condition, that are we leaving the curve or are we along the curve. To ensure that we do not leave the curve, we will take the gradient of g multiplied by d equated to 0, and ensure that d transpose HLD is less than 0 when we are checking for maximum, and when we have to check for minimum, we would do the same calculation, but ensure that this term is greater than 0, and in that sense we should be able to check for minima. So, in this example we will only deal with maximum, and I would request you to look into these calculations for minima as a small homework for you. So, first step to construct the bordered Hessian matrix is that we take double differentiation of Lagrangian with respect to x. Our Lagrange function that we wrote was, I will just write it here again, was x square y minus lambda x square plus y square minus 1 equal, which we wrote as L. So, if you differentiate it 2 times with respect to x, this is what you get. If you differentiate this Lagrange with respect to x and with respect to y, you get 2x. This is symmetric. So, the differentiation with respect to y and x would also be 2x, and differentiation of Lagrange with respect to y 2 times should give you minus 2 lambda. When we put this all together, we end up seeing the Hessian matrix of HL. Understand that this is Hessian matrix of Lagrange and not the bordered Hessian matrix. Bordered Hessian matrix would have certain zeros as paddings to accommodate the gradients of g of x wherever applicable. So, this is our critical point, and these are the elements. So, what we do is that we substitute the values of y star, lambda star wherever we have those particular values. In case of this x star and y star, we also notice that y star was equal to lambda star, as a result of which the first term reduces to 0, del square L del x del y takes the value of 2 root 6 by 3, and del square L del y square takes the value of minus 2 root 3 by simple substitution of values of x and y at the point of interest, or what we call as critical point. This is our critical point. Now, when we substitute this, our Hessian matrix look much neater without notations with these 4 elements, which continues to be symmetric. And then next step is that we also need to determine the feasible directions. If you recall, our feasible directions has this element of g, x, and x is at the critical point. So, what we do is that we take the gradient of our constraint, which is x square plus y square minus 1. When we take its differentiation with respect to x, keeping y as constant, or partial differentiation with respect to x, we get first element of this vector as 2x star, second element as 2y star, then x star and y stars are substituted, we get del g x star y star is equal to 2 root 6 by 3 and 2 root 3 by 3. Now, we have to satisfy this. So, we multiply it with dx and dy, and for this to be equal to 0, because this is the condition to ensure the null space requirement that we already spoke about, so that we never leave our constraint. We equate this to 0 and express dy in terms of dx. So, our D matrix now can be written in form of D is equal to dx, 1 divide and second element becomes minus root 2. Again, when we will multiply, we will try to see that how this dx appears into that, what sign we are getting and so on. And finally, we substitute all these elements into our original equation, which was D transpose Hessian D, and when we do that, we would notice that dx square comes out and these two vectors and one matrix stay inside, which can be multiplied, because throughout our notations we have ensured that we use transpose and in a way that the inner products are satisfied. So, this is 1 cross 2, this is 2 cross 2, this is 2 cross 1. When we multiply all of these together, our end result is of size 1 cross 1. If you recall, in one of the earlier slides, I also was referring to this notation as from an n order real space to a scalar real field, and this is exactly what we are achieving here. So, when we do all this multiplication, the value of this product of vector by matrix and then by vector comes out to be minus 4 root 3 dx square. Now, if dx is real, dx square is definitely going to be greater than 0, in fact greater than equal to 0, and dx is not equal to 0 if I am making a small perturbation, as a result of which dx square is always greater than 0. So, the sign of this term would entirely be determined by minus 4 root 3, which is a negative quantity. Again, recall that whenever we are checking for maxima or minima, the second order sign tells us the maxima or minima in the context that if that sign is greater than 0, we are looking at local minima. If that sign is less than 0, we are looking at local maxima. So, since this value is negative, the Hessian is negative definite along the feasible lines. So, the point that we have calculated indeed happens to be local maxima, which indeed is true, because at that point we had the values higher than the other 2 points that were falling into third or fourth quadrant, again bolstering our point that using this mathematical framework we can now guarantee the sufficiency even in case of constrained optimization problem with equality constraint. Now, let us try to look into the same problem, but through the lens of bordered Hessian matrix. I restate the same problem, x square y subject to same constraint, x square plus y square minus 1 equal to 0. We again construct our Lagrange function in a similar fashion, x square y minus lambda x square plus y square minus 1. We find the roots here in a very similar fashion. Once we do that, we again construct the same cases that we have done. First case gives us x equal to 0, second case gives us y is equal to lambda, for which we find our critical points, and again this is a quick recap of what we have already done. So, I am skipping through these particular slides because this is exactly what we did in checking for necessary condition, because even if you are using bordered Hessian or you are actually checking with direct substitution, the necessary conditions are not going to change. Only difference is going to come in the sufficiency conditions. So, we will check for the critical points root 6 3 by 3, root 3 by 3. This was the point that we already solved for, and even in this case that is what we are going to look at. We recall that the value of function at this point came out to be 2 root 3 by 9, and it was same for the negative of x given x square y. Any argument with negative sign becomes positive and negative on the other side. So, we concluded that maximum value is 2 root 3 by 9 at these 2 points of root 6 by 3, root 3 by 3 and minus root 6 by 3 and root 3 by 3. Then again we construct our bordered, first we construct our actual Hessian matrix before bordering it, which takes the form at that point as a symmetrical matrix of size 2 cross 2, and now we have to border it. This is a new step that gets introduced. Initially we did calculate root g x y and multiplied it with d, but here what we will do, we will calculate this gradient vector of g, take its transpose and fit it here. Without transpose, fit it in the lower part of the border Hessian, and since we only have one constraint in this case, we would have only 1 0 to pad this matrix, and the resultant matrix that we get is called as the bordered Hessian matrix. So, for our problem, this bordered Hessian matrix take the form of 3 cross 3 matrix, and this would always be, one is number of constraint m plus n into m plus n. If you recall, when we were checking for k, we said that k equal to 1 to m and then k is equal to m plus 1 all the way to m plus n. So, we will first look for this matrix, then we will go to this matrix, and finally, we will check for the bigger matrix. This is exactly what we meant by the variations from k equal to 1 to m and so on, that we will keep on finding these lower rank matrices and finally the full rank matrix, and keep on calculating their derivatives, check for the signage multiplied by minus 1 raised to power k, and see whether we are getting the consistent patterns of positive sign or not. So, in this case, our first smallest matrix just comprises of 0. I will just clear this clutter, so that I keep on highlighting what this B is. So, this is the first element 0. The determinant of this matrix is also going to be 0. So, B1 indeed comes out to be 0 in this case. Determinant of B1 is 0. So, I will write D1 as 0. Now, let us go with second matrix D2. Again, I will highlight it in different color. This will comprise of these 4 elements. Now, if I have these 4 elements colored, what I will do is that I will take it out separately, calculate its determinant. You can use your computer, and it is a small matrix, 2 cross 2 matrix. It is much easier to calculate in this case, but feel free to use your computers to calculate the determinant. It comes out to be minus 8 by 3. So, determinant D3 comes out to be minus 8 by 3. Now, if I go ahead, I will calculate the determinant of D3, which is determinant of B. Again, going back to my original matrix, I will color it in different color. Now, all elements have to participate, including the ones in browns and greens. These all will participate to give me B3 matrix. Again, I will calculate its determinant, and I get the value of 8 root 3 by 9. Now, what I will do is that I will see whether their signs are varying or not. So, one thing is that yes, this is negative, this is positive. So, when I will put this into the framework of minus 1 k plus 1 multiplied by b, I am hopeful that I will get all these greater than 0, because I already start seeing that alternating pattern from negative to positive, and this one has to be 0. If you recall, we said that up to number of constraints, all the minors should have 0 determinant, which is getting satisfied, and this is by the property of border Hessian matrix itself, the way it has been constructed. So, no surprise. So, number of variables here are 2, m is equal to 1. So, we will see what k plus 1 should give us. So, when we are at k equal to 2, we will check for sign of minus 1, k plus 1 and the determinant of D2. So, here I get minus 1 raised to power 3, d2 was minus 8 by 3. So, at the end this entire terms come out to be 0. So, my condition is satisfied. When k is equal to 3, k plus 1 becomes 4. So, this value becomes positive, multiplied by the positive determinant again gives me the value. So, for all my points where k is greater than m or k is greater than equal to m plus 1, minus 1 raised to power k dk, this is k plus 1, is indeed greater than 0. That means my bordered Hessian matrix is also positive definite matrix, and when I am looking at these sign of matrices, I can confirm whether my point is maximum or minimum. So, to conclude, what we see is that the bordered Hessian incorporates the constraint into second order analysis. The determinants of leading principal minors help us determine the nature of critical points, and sign of these determinants follow the appropriate criteria confirming whether point is local maximum or minimum. So, one quick clarification: in case of checking the sign of bordered Hessian matrix through this test, the positive signs would give us the indication of maxima and minima, contrary to the values that we see in eigenvalues or pushing along the direction of the curve. So, this again is a mathematical convenience that we introduce, but what is important point here is to understand that properly accounting for constraints is crucial and feasible in the mathematical framework that we are discussing, and two different ways that we have dealt with really provide us the second order checks on understanding these directions of feasibility. Now, going forward, when we will talk about conditions such as Cohen-Tucker conditions and bring in more complexities of inequality constraints, we would not over worry about the second order checks, and we will rely on our computers or Python codes or whatever programming language you would prefer to use to achieve those operations. Going forward, we will primarily focus on the necessary conditions and assume that we have good understanding of checking for sufficiency as and when need will arise, and having that intuition that what these computer codes are doing is important. But as we go forward, we can go easy on the mathematics of checking for sufficiency every time, and our discussion subsequently would typically revolve around finding the critical points and expressing our constraints and objective function in a way that we do not have to worry about these checking for secondary conditions whenever we meet our primary conditions, but this is what we are going to discuss in our subsequent lectures. Thank you.